Welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel for everything I want to talk about science and math. And today we are in AP Chemistry talking about solids. So in this unit we have talked about first gases, then liquids, and now we are to, yes, you guessed it, solids. And I think most of this is going to be a review. Okay, let's see if I've got the draw on. We'll make it red. Okay, so metallic solids. So remember metals, they are hippies. They let their little electrons, they're held together by a delocalized sea of electrons. Remember that from honors? The metals have a sea of electrons, collectively shared valence electrons. So they're not assigned to any one particular nucleus. They just flow wherever they want to in between them. So that's our first kind of solid, is these metallic solids. So name two properties of metals that can be explained by the metallic bonding. They can conduct what? Heat and electricity, right? So, where's my thing here? They can conduct, I'm going to say they can conduct electricity. And we're also going to say that they're strong without being brittle, okay? So the next kind is ionic solids, like salts. What are they held together? What holds together sodium chloride? Opposite charges, cations and anions. So it's the mutual attraction between positive and negative, cations and anions, between ions, okay? So can an ionic substance in the solid phase be a good conductor of electricity? Does salt as a rock conduct electricity? No. I saw somebody mouth it. No, it cannot. And we did this in the lab in honors. We took our little probe, we stuck it in the salt, it didn't light up. We took the salt, we poured it in the water, we stuck it in there, and it lit up. Did y'all do it in Corn's class too? Did y'all do the conductivity lab? I got that one from Miss Weeks. That's a good one for knowing the properties of ionic and covalent. Okay, so no. To conduct, and the reason why is to conduct electricity, you need your electrons or ions must be able to flow. In a crystal lattice, they can't. They're all stuck. So they have to be dissolved in water or something like that. Oh, I got to the next part. In order for an ionic substance to behave as a good conductor of electricity, it must be molten, which means you melt it. So can you melt salt? Yeah, if you get it hot enough. And so somebody was asking, well, like, could you do that at your house? No, you're not going to get anything hot enough. It'd be in a lab, in an industrial complex, someplace like that. Or you can dissolve it in water, and then it conducts great, okay? Our third kind of solid is the covalent network solids. And these are held together by an extended network of covalent bonds. So this would be like diamonds. So what do we know about diamonds, other than they're expensive and pretty? What are they known for? Being strong and hard. It's the hardest substance. There are things that only a diamond can cut. So that's why you can buy at Home Depot, you can buy saw blades that are diamond tipped. So they cost a lot, and they're not jewel grade diamonds, they're industrial diamonds. Not all diamonds look like that. So the next one is molecular solids. So this is like wax, things like that, things that are covalently bonded. But then they are held together by intermolecular forces. And I on purpose use the abbreviation because you need to know that IMFs are intermolecular forces. So you're not taking the AP test and go, IMFs, I don't even know what this is talking about. Yes, you do. Intermolecular forces. London, dipole, dipole, hydrogen is what holds them together. Okay, not very strong. So what is a property? So the diamond goes up with that one. What are properties of molecular solids? So like an example of this would be like wax. That's one of the ones we did in that lab in honors. So what do we think about wax? Is it hard or soft? It's soft, right? They're more soft. And does wax have a high melting point or a low melting point? Low. We melted it in wax, and the wax in lab. We melted the sugar. We melted the wax. Okay, so here are some examples of our 4 kinds of solids. A metallic solid could be copper or iron. That's a good one. Ionic solid, you always think of salt, right? Sodium chloride, and then it could be something else like magnesium oxide. That's a good one. A covalent network solid could be like carbon in a diamond or silicon. It's a very pretty rock. A molecular solid, we could say hydrogen bromide, or even like water if it's frozen is a molecular solid, so we'll put S. Solid water, otherwise it's a liquid and it's not a molecular solid. It is a liquid at that point. Okay, good so far? I told y'all this was easy. This is some easy stuff that you pretty much know, but just in case, I decided we better go over it. Crystalline solids are solids in which atoms are arranged in an orderly repeating pattern. Okay, name 2 examples of crystalline solids. That'd be your salt, sodium chloride, and another one, and I need to make myself a little note, is silicon dioxide. Miss Raymond, which is quartz, Miss Raymond sent me a really cool video from TikTok about that, about silicon dioxide and its hydrophobic properties. And I was like, oh, I'm going to show it to the kids. But then, 3rd period, I forgot. So I'm not going to show it to y'all because I don't want y'all to get ahead. Well, wait, I'll try to remember to show it to you tomorrow. Okay, so how are amorphous solids different than crystalline solids? Amorphous means without a shape. So they lack the order found in crystalline solids. So example would be like rubber and even glass. Glass, if you could look at it, you know, under a strong enough microscope and see the atoms, then you would see they're not in nice little orderly crystals. So there's my rubber. It's all squishy, like flubber. That's my little drawing of it. Okay? So there's a lot of information in this chapter that's not on the AP test, and I tell you, it's not on the test in your notes, not to study it. And one is these names of all of these little crystals and unit cells. So I really thought y'all were going to have to learn them. I think last time I taught AP, the kids had to learn them. I think it's one of the things they've changed about it. And y'all can be glad about that. Okay, so metallic solids. So we talked a little bit about more of those. Now we're going to go back to metals for a second. So metallic bonding results from the fact that the electrons are delocalized, is what they say. I say they are allowed to run wild and free, like little hippie children. They are delocalized throughout the entire solid. So a clean metal surface, as a result, has a characteristic luster. So you know how teachers can have their, or anybody has for their email like a little signature that's always there. So I saw one chemistry teacher, and instead of having like what they taught or whatever, it said, everything that glitters is not gold, but it has free electrons. So now y'all understand their little signing. That it has these characteristic luster or glitteriness, shininess, because it's got free electrons. And those free electrons give it its characteristic luster. It also makes it where it's good conductors of heat and electricity. It makes it where they're malleable, which means they can be hammered into thin sheets like aluminum foil. And it can be ductile, which means they can be drawn into wires. That's what those words mean. So, next part of the chapter, you can skip. And then we're going to talk about mixing metals together. What's it called if you take metals and you melt them and you mix them together? It starts with the letter A. Alloy. I heard somebody say it. An alloy is material that contains more than one element and has the characteristic property of a metal. So if 2 different atoms have similar atomic radii and chemical bonding characteristics, it's called a substitutional alloy, which forms, that can be formed in which atoms of the solute occupy a position that are normally occupied by the solvent atoms. The example is silver and gold. Okay, so let me translate this for you. Okay, so you melt these metals. They're hot and liquid. You mix them together. They cool, and you get a new alloy. So example is 14 karat gold. That's not pure gold. It's a mixture of gold and silver. So whenever you mix stuff, you have a solvent and a solute. And when I taught that to you in Unit 8 of Honors, I taught you that the liquid, like water, was the solvent, and the solid, like Kool-Aid, was the solute. Do you remember that? But these are both the same. They're both melted metals. So how do you know which one is the solute and the solvent? And if it is a substitutional alloy, that's the one that you have more of. So 14 karat gold is more gold than silver. So gold is the solvent, silver is the solute. Everybody follow that? But that's not always the case. And that's our next one. Okay? Interstitial alloys, that's fun to say, can be formed. And this time, so the molecules are about the same size, the atoms are. But this one, you have a small atom and a big atom. So the smaller solute atoms fill the spaces between the larger solvent atoms. So with this one, it's which one has the bigger atoms is considered the solvent. The one with little atoms is called the solute. Okay, and so a lot of times it's a small nonmetal being mixed with a larger atomic atoms of metal. And that's how they make steel, carbon steel. They take iron, which is big atoms, and mix in carbon, little atoms, and you get stainless steel. Better than iron. Better than carbon for making a knife, right? Okay, does that all make sense? We're good on that? Okay, good. All right, next thing, metallic bonding. So we'll talk a little bit more about metal bonds. So there's a 8 minus n rule, which the number of bonds that an atom normally forms with its neighbors equals the number 8 minus the valence electrons. Okay, so following this rule, argon, 8, how many valence electrons does argon have? 8. What is 8 minus 8? 0. So how many bonds does argon make? 0. Follow how this works? Okay, so chlorine. How many valence electrons does chlorine have? 7. What is 8 minus 7? 1. So how many bonds does chlorine normally make? 1. Still following? So let's do another one. Sulfur. How many valence electrons does sulfur have? It's got 6. What is 8 minus 6? 2. So how many bonds does sulfur normally make? In oxygen, that whole family, 2. Okay, phosphorus. 8 minus 5 is 3. Phosphorus and its whole family, nitrogen, they normally make 3 bonds. Right? So let's try silicon. 8 minus 4 is 4. So silicon, carbon, that whole family makes 4 bonds. Well, let's look at aluminum. So aluminum would be 8 minus 3 equals 5. In your chemistry life, have you noticed aluminum always making 5 bonds? No, I see people saying no. So what's going on? Question mark, question mark. Okay. Does aluminum form 5 covalent bonds with its neighboring atoms? No. See, you do get to learn something new today. That was it. And maybe a little bit about the different kinds of alloys. Okay. So this is what's going on. Metals don't have enough valence electrons to satisfy their bonding requirements with electron pair bonds. Instead, valence electrons are shared between atoms in a crystal lattice. So there's my aluminum, little piece of aluminum, nice little lattice. If I got a little bitty piece of my aluminum foil, you can see it. So draw a picture similar to figure 12 21 and discuss the details of the electron C model. Explain how the properties of electrical conductivity, malleability, and ductility can be explained by this model. Okay, so this is what it could look like if you could get into your even smaller microscope. That you've got all the nucleus, the nuclei, and around them is just this big sea of electrons. And they flow wherever they want to. They're just in these clouds in between all of them. But notice that the nucleus stay in the crystal lattice. They stay orderly. But the electrons, they're not orderly at all. So this affects these things. So electron conductivity. Why does this model explain conductivity? The electrons can flow wherever they want to through the sea, and if it's hooked up to a battery, it's going to go to the positive terminal. Or if it's an outlet, the wires are, the wires is going to go to the source of electricity, and these electrons are going to be attracted to that positive source, and they're going to flow toward it. Okay, so that's why it's electrically, why they can do conductivity for electricity. Now, why do the electrons conduct heat so good? Well, it's because they're moving. They're just moving wherever they want to. And the electrons can respond to and transfer kinetic energy. They're already moving. Here's this energy, they can respond to it, and that energy can go through the solid very easily. So it transfers heat. Metals are good conductors of heat and electricity. Now, why is it? Oh, I told you that thing does not flip good. Okay, now I'm going to be real good this time and not turn my camera upside down. Last time, halfway through, I flipped it, so the rest of the video would have been upside down. Okay, we're going to have to use some gas laws here and cause a suction. I'm going to decrease volume and increase pressure. So that'll stay on. All right, get back on there. This makes for very good YouTube watching. All right, you stay right there, buddy. Okay. Last time that happened, I turned it upside down. I did. So it's great, more technical. Okay, malleability and ductility. Okay, so the electrons easily redistribute. They easily redistribute. So like, say you hit this. You can think of these electron clouds as squishy. And so you hit it, it's not going to break, it's just going to squish and get flat. Or if you start pulling it out, it's all squishy. And so you can just pull it into a wire and it's not going to break. Do you follow that? It's the squishy property. So there's my sea of electrons. Okay, can I scroll? We good to scroll? Okay. All right, so the next one is ionic solids. Ionic bonds are very what? Weak or strong? Strong. They're real bonds. They're not intermolecular forces. They're real bonds held together by a positive and negative, very strong force of attraction. They're strong. But then why do they break so easy? If I took a hammer and smacked my crystal salt lamp over there, it would shatter, wouldn't it? How come? If they're so strong, this thing shouldn't be breaking like that. Well, it's because of this, okay? Here I've got my crystal lattice of sodium chloride. Sodium chloride, sodium chloride, cations and anions. And they're being held together by attraction. But what if I push right here? Here's my hammer, bam, and I hit it. Then the crystal is going to slide over. It's going to go over, so we're going to put slides. And then it's not aligned right anymore. Instead, you've got like charges next to each other. And what do like charges do? Attract or repel? They repel. So not only does my salt lamp break, it explodes. Because I'm going to have this big force of repulsion causing them to repel against each other, and they're going to repel and explode. So now you know why if you hit a salt lamp with a hammer, it's just really going to do some breaking. Okay, can we go on? Now, molecular solids. So these are ones that are covalently bonded. Molecular solids consist of atoms held together. So the atom itself is covalently bonded. But what makes the molecule itself? But what makes the different molecules stick together? Only London dispersion forces, dipole-dipole, and hydrogen bonds. So the molecules are strongly held together, but they're not strongly held to each other. So explain why molecular solids are soft and have relatively low melting points. And the reason why is because these attractions are weak. They are not strong, they are weak. So, but what about sugar? Okay, so like if I think about wax, yeah, I can see that it's soft. But isn't sugar crystals? Like even on the sugar bag, it says Dixie Crystals. You've ever bought the Dixie Crystals sugar bag from Savannah? They have a sugar plant in Savannah making Dixie Crystals. Well, they're little crystals, aren't they? But they're not supposed to be. This says that they're not crystals, that they are soft and weak. But sugar crystals are kind of hard, aren't they? So this is what it is. Each sugar molecule has, let me find my little paper here, 8. That's a whole bunch. OH groups, which cause what kind of intermolecular force? Yes, hydrogen bonds. And so like intermolecular forces are weak, but if you get enough of them, they can get pretty strong. So 8 hydrogen bonds is a bunch for every single molecule, and so that gives it that crystal, where it looks like salt, but it's not. Which one dissolves in water fast? The salt, not the sugar. Which one melts? The sugar, not the salt. So it's still this molecular solid, but it kind of can fool you because it's got so many hydrogen bonds. Okay, so the next one is our covalent network solids. This is like our diamonds. Why are covalent network solids much harder and have a higher melting point than molecular solids? They're both made out of covalently bonded molecules. Why is this one hard and that one soft? And the reason why is it is much stronger than intermolecular forces. So they are actually held together with bonds. They're covalent bonds, but they're bonds. So our examples like silicon, germanium, quartz, silicon carbide, boron nitrate. We got some examples. But one that we want to talk about is graphite versus diamond. Okay? So graphite is what's in your pencil for your pencil lead. It's not really lead. If it was, if you licked the end of your pencil, you'd be a little stupider because lead causes brain damage. We couldn't have that in kids' pencils. It's graphite. It's carbon bonded in these sheets. Where diamond is carbon, the same exact thing, but it's bonded in tetrahedrals instead of sheets. Okay? So this is our graphite in our pencil. It's sp2 hybridized sheets. So 3 bonds, each carbon has 3 bonds. Each one has that trigonal planar shape. Do you see that? The layers slide past each other easily because there's nothing in between them except intermolecular forces. There is no bond between these layers. Okay? Instead they have delocalized pi bonds, and the electrons can flow through those pi bonds, so graphite can conduct electricity. Anybody ever seen those videos on YouTube? There's this one guy, and he's always attaching things to a pencil to make the electricity go through it, but he doesn't follow lab safety, and he's always getting burned. And it'll blow up in front of him. He puts too much electricity through it. It's got too many amps, and so he's blowing these pencils up thinking, so anyway. So it can conduct electricity, but it does have resistance, okay? So for the diamond, each one of these are bonded with covalent bonds in a tetrahedral. So these are sp3 hybridized, 4 bonds. They're covalent bonds, and they're very strong. Diamond is extremely strong. It's covalent, but extremely strong. Okay? So don't let that confuse you. Now, in particular, we want to talk about the element silicon. okay, because it's really important, because it's computers and cell phones and all that. It's a covalent network solid and a semiconductor, okay? Now, so silicon, if it's all pure, does not conduct electricity. But they can do something that's called doping, which I think is kind of funny. It's like giving the silicon a little drug so you can turn it into a computer, okay? You dope it. So what they do is they take a few, they mix into the crystal lattice, so it's not all pure silicon, something else. One of the things they can mix in is phosphorus. And phosphorus atoms have 5 valence electrons, and silicon has 4. Everybody see that? So if you put this phosphorus in the crystal lattice, it has an extra electron floating around that can increase the negative charges, and it is conductivity. Now this is called N-type for the extra number of valence electrons, and it's got negative charges, so this makes it conduct electricity. But the reason why we like silicon is not because we can make it into a conductor, it's that we can turn it on and off. You know, most conductors like copper wire, theirs is on. You can't make them not conduct electricity. Silicon, you can turn it on and off. You can turn it on by putting phosphorus in there. You can make it where it has breaks in the conductivity by adding aluminum. Aluminum has 3 valence electrons, but silicon has 4. So it creates a little place where there is nothing, where there should be an electron. And they gave it a very scientific name. They call it a hole. There's a little hole where there's supposed to be an electron. And so you can think of it like as a little positive place. So this is called p-type for positive. And the hole can move around the lattice because an electron can jump in the hole and then it's filled and it's not a hole anymore. But wherever the electron jumped out of, it left a hole behind. So they can use this to turn on and off the electricity, and now we have computers as a result, and cell phones and everything else. So great. Okay, the last couple are not on the test. They're interesting, they're fun. Not on the test, we're not going to study it. You've got 45 minutes. I want you to work on your book work. You've got book work on Canvas for chapters 10, 11, and 12. You can start wherever you want. The chapter 12 book work is particularly easy. All right, science is great.